need to generate creative stories, or perform technical analysis, all while keeping the right balance between imagination and precision. We'll see how to configure FastMCP tools to dynamically switch between models based on the task, using high-temperature settings for creativity and low-temperature settings for consistency. The pattern also shows how to specify model preferences, ensuring the right LLM handles each job. At MCP Tool. Async Def Creative Writing Topic. SDR CTX. Context. SDR. Generate creative content using a specific model. Response equals await CTX. Sample. Messages equals F. Write a creative short story about topic. Model preferences equals Claude 3 Sonnet. Hash prefer a specific model. Include context equals this server. Hash use the server's context. Temperature equals 0. 9. Hash high creativity. Max tokens equals 1000. Return response text. At MCP Tool. Async Def Technical Analysis Data. SDR CTX Context. SDR. Perform technical analysis with a reasoning-focused model. Response equals await CTX. Sample. Messages equals F. Analyze this technical data and provide insights. Data. Model preferences equals Claude 3 Opus. GPT-4. Hash prefer reasoning models. Temperature equals 0. 2. Hash low randomness for consistency. Max tokens equals 800. Return response text. This demonstrates the context-aware LLM delegation pattern, where tools dynamically offload specialized tasks to language models while maintaining execution context. The pattern treats LLMs as modular capabilities that can be invoked declaratively, with the framework handling model selection, context propagation, and response handling. What makes this distinctive is the separation between task definition and LLM execution, allowing tools to focus on orchestration rather than implementation details. The approach works through declarative sampling requests that encapsulate both the task requirements and execution constraints. Tools specify what they need: creative generation versus technical analysis, how it should behave, temperature, token limits, and which models to prefer, while the context object manages the actual LLM interaction. This creates a clean abstraction where tools define intent through parameters, and the framework handles the variability of different LLM providers and client capabilities. This pattern solves the problem of tightly coupling tools to specific LLM implementations or client environments. It enables server-side tools to leverage client-provided LLMs when available, fall back to configured providers when needed, and maintain consistent behavior across different execution contexts. The trade-off is slightly more complex configuration for significantly greater flexibility, making it ideal for multi-tenant systems, hybrid AI architectures, or any scenario where you need to decouple tool logic from LLM dependencies. Let's break it down line by line. At MCP Tool. Async Def Creative Writing Topic. SDR CTX. Context. SDR. Generate creative content using a specific model. This defines an AI callable tool for creative writing tasks. The @MCP tool decorator exposes it to models, while the type hints and docstring automatically generate the tool's schema. All FastMCP tools should accept the context parameter for logging and progress reporting. Response equals await CTX. Sample. This invokes the FastMCP sampling engine asynchronously. The CTX sample method handles the actual AI model interaction, managing the request lifecycle from prompt construction to response generation. All tool functions delegate to this core sampling mechanism for consistency.
Messages equals F. Write a creative short story about topic.
This constructs the prompt string for the AI model. The F string dynamically inserts the user's topic into a creative writing instruction, ensuring the generated story stays relevant to the input while maintaining a consistent prompt structure.
Model preferences equals Claude 3 Sonnet. Hash prefer a specific model.
This specifies the preferred model for this tool invocation. By explicitly setting Claude 3 Sonnet, it ensures consistent creative output quality while allowing fallback to other models if the primary is unavailable. The pattern mirrors FastMCP's model preference system, where strings indicate strict preference and lists indicate ranked alternatives.
Include context equals this server. Hash use the server's context.
This enables server-specific context injection. The this server value tells FastMCP to include the current server's contextual data, like recent messages, user preferences, or server-specific rules, in the model's prompt, ensuring responses stay relevant to the active environment. Critical for tools that need serverware behavior.
Temperature equals 0. 9. Hash high creativity.
Temperature controls randomness in model output. A value of 0.9 maximizes creativity by increasing output variability, ideal for generating diverse story elements. This prevents predictable, formulaic responses in creative writing tasks.
Max tokens equals 1,000.
Max tokens equals 1,000 enforces a hard limit on response length, preventing runaway generation and controlling cost. In creative writing contexts, it balances sufficient room for narrative development while maintaining predictable output size. This is standard practice when calling LLM APIs to avoid unexpected token usage spikes. This closing parenthesis terminates the CTX sample call, finalizing the AI request configuration. It packages all parameters, model preferences, temperature, and context into a single API call that executes asynchronously. The pattern ensures clean, atomic requests with all settings explicitly defined before execution.
Return response text.
This extracts the generated text from the AI response object. FastMCP always returns structured responses, and text accesses the raw content while ignoring metadata like usage stats or warnings.
At MCP, tool. Async def technical analysis, data, SDR CTX, context, SDR. Perform technical analysis with a reasoning-focused model.
This defines an AI callable tool for technical analysis, marked by the @MCP tool decorator. The context parameter enables logging and progress tracking, while the docstring becomes the tool's schema for AI discovery. This pattern ensures all tools maintain consistent interfaces for model interaction.
Response equals await CTX, sample.
This invokes the model sampling operation through the context object. The await CTX, sample, call handles the async communication with the AI backend, managing the request lifecycle from prompt submission to response handling. All model parameters and preferences defined above are passed through this single call.
Messages equals F. Analyze this technical data and provide insights. Data.
This constructs the prompt string for the AI model, embedding the input data directly into the instruction. The F-string format ensures dynamic insertion of the technical data while maintaining a clear, structured prompt that guides the model's analysis focus.
Model preferences equals Claude 3 Opus. GPT-4. Hash prefer reasoning models.
This specifies a fallback model hierarchy for the AI task. When Claude 3 Opus is unavailable, it automatically fails over to GPT-4, ensuring consistent execution without manual intervention. The ordered list pattern guarantees predictable fallback behavior for critical operations.
Temperature equals 0. 2. Hash low randomness for consistency.
Temperature controls output randomness in language models. Setting it to 0.2 enforces deterministic, consistent responses for technical analysis, where precision matters more than creativity. This prevents unwanted variability in analytical results.
Max tokens equals 800.
This limits the response length to 800 tokens, preventing incomplete outputs and controlling API costs. For technical analysis, where precision matters more than creativity, shorter responses with focused insights are optimal. This closing parenthesis terminates the CTX, sample, call, finalizing the AI request configuration. It signals the end of parameter specification before the awaited response is processed.
Return response text.
This extracts the generated text from the AI response object. All FastMCP tool functions must return strings, so this final step ensures the raw text content is passed back to the calling system. Model preferences pattern. The code demonstrates FastMCP's model preference system, where tools explicitly declare their ideal LLM backends through model preferences, either as a single model string or a prioritized list. Temperature settings create an inverse relationship between creativity and consistency that you must consciously balance for each use case. This pattern transforms model selection from a global configuration problem into a tool-level design decision.
The tool that names its model becomes nameless to all others.